Greetings, Professor. We're from Group B. We're going to present modern cryptography, which would include RSA and AES. These are the table of contents that we're going to cover for today. The most important part are the implementation of RSA, AES, and lastly, we're going to cover our project on the front end as well. So our goal is to implement asymmetric encryption and symmetric encryption from scratch. That's why we choose RSA and AES. And we're going to test our cryptography with a user-friendly web interface, React. And our backend is going to be Flask. And we're also going to compare our project with the industrial standard as well. So the two pillars of modern cryptography are RSA and AES, as you may know. Our implementation is for RSA is going to cover four main bit keys: 256, 512, 1024, and 2048. But for AES, our implementation is going to cover 128, 192, and 256 bit keys. And the reason why we're going to implement both RSA and AES because when we combine both of them together, we get like a hybrid systems that has RSA for key exchange and AES for data, because we know that AES is very fast for large data, and RSA it can be slow, but it just enables key exchange. We want to verify our scope and limitations for our project. This is just for educational purposes only, and it's not applicable for production. So we're not going to cover OAP or any PSS. And for our AES cryptography, we're not going to cover electronic codebook as well. And we're going to have a limitation in in-memory key storage. Um, so a trade-off for our project is that we're going to have a pure Python implementation, and it's it doesn't have like any hardware acceleration, and it just has a single-threaded operation only. So this is just the 5 key math components that we're going to use for RSA. The number theory behind RSA are just Euclidean algorithm, which is TCD. We're also going to use extended Euclidean algorithm as well. Then for modular inverse, we're going to use it to make RSA work. And we included in our RSA underscore system Python file. And we also have a Miller-Rabin formality test, which includes 5 rounds of K. And so what we solve is for probabilistic testing. So it's not deterministic, just like the industrial standard. It's just allows us to find large prime quickly. And for our prime generation, we tested with Miller-Rabin test, and it's very random, but it is cryptographically secure because we use secrets module. This is just a summary table of the operations in RSA, and we also include the complexity behind it and the purpose that we're going to use in RSA. So the main part is when we find the private key, we're going to use extended GCD. These are just the security guarantees for our number theory. We have all the mathematical invariant tested in our unit tested file.
And so when it comes to the mathematical foundations for AES, we use Galois field theory. And so it's basically just a finite field structure with 2 to the power of 8 elements. So 256 elements, where for each number that is represented by a byte that represents itself a polynomial of degree less than 8, We use operations on these to perform addition and multiplication, as well as using the irreducible polynomial to make sure that for each operation, it stays inside of this field. And so we construct the S box, which is a very important aspect of AES because it provides nonlinearity. It is the only layer of AES that provides this nonlinear element.
This is the architecture behind RSA. We have a three-layer design. We can start with layer one for all of the core cryptographic classes for RSA, and that would include the Miller-Rabin primality test in prime generator, and the core operations would be in the RSA class. And the second layer would be all of the simplified API that we're going to send to the REST API and Flask in layer three. These are just the 5-step algorithm for the key generation process. It's going to be covered thoroughly in the next page. So for the first step, we want to choose two large primes, P and Q, and we have all of the security check. Specifically for primes, we want to make P and Q a distinct number, and it has to be cryptographically secure randomness. And the step two is to compute modulus. We want to ensure that n is hard to factor and n is public. And for step three, we want to compute Euler totons. That would mean phi n. And it's very critical for RSA because we want phi n to be kept a secret, and we wouldn't want it to include in public or private key exports. So it has to be used to compute the private key D. For step 4 and step 5, it's basically to choose a public exponent and the private exponent. For the public exponent, we choose E equal to 65,537, which complies with the industrial standard. And it ensures that the modular inverse exists. And for the private exponent, it's just to ensure that D is kept absolutely secret. So we have like a table that includes the performance of a key generation process for all of the key bit size, and all of the tests will be covered in our unit tested file to ensure that it's secure.
So for key generation, our RS equation process involve use of enter plain text through the front end, and the front end will send the plain text through the APIs for equation, or the backend now convert the text to base, and the bill being converted also into an integer, and then being verified, checking that the message should be less than the model. And then also we compute the server test. The backend return a Hessian cipher test, and the UI display the cipher test without clearing the plain text. So the purpose is to show RSA confidentiality works with a public key. So for the equation process, user enter the server test created during the equation process, and then which will be sent to the backend. The backend will now convert the Hessian into an integer, and then compute the plain text through the formula MC to the D more, which then returns the decrypted text to a separate output panel, which is on the front end that will be demonstrated later. And then the UI compares the decrypted text with previously created plain text, show match in order. So the purpose is to verify correctness of our RSA round trip. So we also have our digital signatures implemented. So signing step implemented involve input message provided by a user, and the backend then convert the plain text into a 266-bit hash message, and then with a signature be generated, which return a signature in the hashing format. The UI also displays the signature in the signature panel on the front end. And the purpose is to demonstrate message integrity and authentication. For verification purposes, the logic implemented, the front end sent message plus the signature that was signed through the signing process, and then what the backend also recompile the 256 bit message that were created, and then send a verification through the formula that being used, V equal S E M. The more of N, the V is have to do with the recovering signature, the S, the signature, and the N is the modulo, the E is the exponent in this formula. So we check if V is equal to the hash message that was signed. And then if the message is the same message that was sent, the plain text now will be the front end will return valid, or if there's any alternation or alteration into the text that was the signature that had been signed, we also return invalid, So which tells that something wrong with the signed message. So our purpose is to confirm that message was signed with a correct private key, and then message has not been altered as well.
Now let's talk about the algorithm design and architecture for AES. So first of all, I would like to say that we coded AES, the AES algorithm purely using Python without any external libraries, because those are usually written in C to make it faster. And so the data is processed in 128-bit blocks because AES is a block cipher. And so we follow the substitution permutation design, meaning that we have variable rounds based on the key size. So for 128, 192, and then 256-bit key size of AES, you have different number of rounds, 10, 12, and 14 respectively. And now let's talk about the key expansion and round operations. So the key schedule for AES is pretty straightforward. You start with an initial key, and then you derive a separate key from the original key with different lengths. And basically you add that to the cipher at the end of each round. So each round consists of subbytes, shift rows, and mixed columns, where the subbytes is just you substitute using the S box, and then shift rows, you shift the rows of the matrix, and then you mix each column of the matrix, and then at the end you add the round key on top. And you do that each time. And so for modes of operation, we implemented it in the electronic codebook mode. This basically means that we separate the plain text into blocks, and each block is encrypted independently, meaning that with the same plain text, you will get the same ciphertext, which is not exactly secure, but since we are using it for educational purposes, it makes it easier for us to understand. And now let's talk about some implementation details. So these are just helpful functions that was used, like the pad and unpad functions was used to pad the length of each block to make sure that it's the same size. And the design of our API was pretty straightforward. To make it simple, we just had the encrypt, decrypt, and generate key that was exposed. And yeah, that's it.
Right, so now let's talk about the user interface and application indications. For this page, we are talking about the system architectures. We decided to go with the client server models because it's provide a clear separation between user interface and backend logics. With that, we decided to go with the single page applications because it is dynamic and responsive and yet it's lightweight. And for the communication, we are choosing RESTful APIs. It's a standardized communication protocol between clients and servers. Let's go deeper into the client side or the front end. For the technology, we're using React.js, and for the styling, we're using Tailwind CSS. So for the clients side, it's responsible for rendering the UIs, such as the interactive forms, buttons, and display areas, and it also do a state management to handle user input selections, loading different messages, errors, or any answers. And it does an API calls to initiate like requests to the Flask backend using fetch API, fetch call. It also do a basic input validation to check if the inputs are valid to do certain things. So for example, if we haven't inputs the key or plain text, we could not encrypt anything. So the button will be disabled. And for the server side of the backends, we are using Python Flask as mentioned by our teammates, and it is responsible for exposes the route for AES and RSA operations. It does a core cryptography functions such as encryptions, decryptions, and key generations. It also stores RSA key per session ID temporarily on the web, and it also do a error handlings by providing informative error messages to clients or to the front ends to the users if something goes wrong. So for the integration between the front and the back ends, the key point is that the front end will talk to the back ends, and then we talk to the back end using the RESTful APIs that just mentioned. So the React or the front end will send an HTTP request. In this case, could be an encrypt, decrypt, or generate keys with adjacent data Flask. The Flask role or the backend role will receive the request and then perform an actual functions on it. If an encryption, it does a encrypt. If it encrypt a request, it will does encryptions and so on using our custom Python implementations. And once it's done its calculations, it will send back the response. If it's an error, it will send back the error message. So the benefits is that it has a clear separation of concerns, the backend in one locations and the front end in one locations, and our teammate can just focus on their parts separately. So let's just do a quick demonstration of the website itself. So for this one, we're doing a AES encrypt and decrypt. So as you can see, there's many sites you can select. For this example, I will do the 192 and then I will generate a key. And I got a key, I can then input a plain text. So, hi, this is a dog. And then I would encrypt it. And this is the encrypted key or message basically. And then if we want to see that if these are right things, we can just go back to the crypt and then put in the encrypted keys or the cipher text, and then we want to decrypt it. You can see that the decrypted text is hi, this is dog, which means that our calculation is correct. And the same goes for RSA, even though this one is a bit different, but you will see why. So it has a bunch of options for you to go through. For this one, I just go to a 1024 bits, and then we want to generate the key. And just input the context. Hi, this is a cat. This okay. And then we encrypt it. So you can just copy the clipboard, go to decrypt, pass that in, and decrypt, and you can see that this is our message. For the digital signatures, sorry, because we already just restarted. Okay, then you can select just like the RSA, Let's just go with the 2048 bits, and then we want to generate key. Give it a second. Okay, once it's generated, you can just do a message to sign. Just put hi, and then I sign this message. So if I want to verify, I can just go back to here. This will be automatically populated. You can just enter the original message. So if I say TT and I'm trying to verify, it will say the signature is invalid because this is not our original message. Our original message was hi. And as you can see, it's valid. And that's it for the website itself.
So this is just a summary of our security analysis of the entire project. We ensure that our project follow all of the mathematical correctness, and our formality testing is going to have 5 rounds. And in the production standard usually has at least 40, and for some general standard would have 16 rounds as well. And we have secret modules as for the cryptographic randomness, which is the same as production standard, except some production standard would have a different one called CSPRNG. And we ensure that our project complies with all of the input validation, just like normal production standard. And our signature hashing would be SHA-256. That's the most famous and secure hash. But for the other aspects, such as padding with OAEP, optimal asymmetric encryption padding, or the heading in the signature, digital signature, we're not going to cover PSS just like the production standard. And for our AES mode, we only have in ECB only electronic codebook, but we don't have the general production standard either. And for the timing attacks and side channels, it hasn't been mitigated for our project for now. So for the unit testing for RSA, we have a total of 46 unit tests, which is going to covered under the RSA directory.
Okay, so let's go on to the integration testing. So the purpose of doing the integration testing is to verify the different components. For examples, the front end, the back ends, the modules are working together as expected. And the tool that we use for the testing are the Python unit test modules, which is a standard library for creating your structures, test suites, and a Flash test clients to simulate HTTP requests for the Flash API without running a full server instance. For the scope of testings, for RSA endpoints, we're having 4 tests: the key generation, encryption and decryptions, digital signatures, and key retrievals. And for the AES endpoints, we'll do 3 tests: key generation, decryption and encryptions, and error conditions, such as missing fields or invalid ciphertext or keys. Direct.
And so here is the AES unit testing. So we have a list of all the functions and inputs that were tested for AES algorithm. In green, you have the name of the function itself and a short explanation. So we tested everything from the encrypt decrypt functions of all the sizes to empty strings and different formats and lengths of keys that could affect the AES algorithm.
So this is just a summarized performance metrics of both cryptography. We have found 2 main key findings from both cryptographic algorithms. So the key finding in RSA is just that decryption is 46 to 96 slower than encryption because of the private key operations. But for AES, the the operation only takes the decryption is only takes like 2 times slower than encryption. But we have to be ensured that symmetric cryptography can be significantly faster than RSA, so that is no problem at all. So these are just the graphs for performance metric in RSA, and the next one would be for AES. As for the throughput and the comparison with standards for the industrial standards in general, our project has implementation of pure Python, just like our teammates have mentioned. We don't follow the standard libraries that the production standard would use, like OpenSSL, PyCryptodome. And the reason why our implementation can be 5 to 10 times slower than the optimized libraries that the industrial standard use is because we don't have the hardware acceleration, just like we have presented in the scope limitation. That's just because we want a project to be educational purposes only. So, and that's why we don't have the Chinese remainder theorem optimization as well. Next, please. Yep. So we have some performance bottlenecks, especially for our RSA. All of them are just in pure Python modular exponentiation, so we don't have any parallelization like the production standards. And for the AES, we don't have any specific hardware acceleration, just like the new instruction in AES. So our electronic codebook loops can be quite inefficient compared to the production standards. And we also don't have any memory efficiencies. So the known issues that we have is just that the project we have don't have any critical bugs. It's just that we for the formality test, specifically for RSA, we only have like 5 rounds of formality tests. And the production would need like at least 40. Some general tests would actually be 16.
So the main feature implemented in the project, this is a summary of the overall projects. For the backend, RSA key, we generated RSA key by using PQNED. We also encrypt and decrypted plain text to cipher text. We have our digital signatures, and we also verify the signatures that were signed. We have a session-based key storage. We use a clean JSON API for front end. So for front end features, we have 3 tabs for RSA interfaces, which is we have the key generation, we have the decrypt and encrypt, we have the sign and verify. We displace our keys value and fingerprint, clear verification error messages, or persisting plain text during equation and side-by-side equation and decryption panels. Signature panel for testing were also integrated. And key takeaway from the RSA perspective, we integral conversion, we have a byte encodings, we have a live prime generation, error validation. For UI, UI needs to reflect cryptographic workflow. Back end and front end must communicate precisely for cryptographic purposes, and importance of separating private keys generation and public key generation. Overall, we learned how RSA actually worked under the hood and not just using library. So for future work, as it was said by my colleagues, this is just for class purpose and education purpose only. So we have more limitation that were discussed. So these are features that can be added to our projects, and security improvement. To the RSA, we can add some polling or OAE P equation, which make equation more safe, and because they generate some randomness, and PSSA that provide a secure key that difficult to fetch also, and also some features of extension. We might import and export keys in a PEM format out of file encryption or digital signatures on file. Compare RSA and ASE performance in the real time. We can add a visual diagram for key generation and equation flow. For the user interface improvement, we can also add a progress indicator during prime generation or syntax highlighting for large numbers. We can have a team of dark or light mode for accessibility. So this comes to the end of our project. We want to use the time to say thank you to everyone, to my colleagues, and to Professor Zeng for the opportunities given us in this class, and the opportunity to make a real work project to test our skill in cryptography. And I want to thank everybody for the hard work. Thank you.